Hi, welcome back. In our previous lesson, we looked at consumer optimization where we focused on corner solution. Today, we'll be moving on to utility. We mentioned in the previous lessons that the consumer's goal was to reach the highest possible indifference curve given their budget constraint. Hence, the consumer's objective is to maximize the value of her utility function subject to her budget constraint. Now, the notion of utility also allows us to reinterpret the necessary condition for utility maximization. So, to do this, let's begin with the definition of marginal utility. Marginal utility is the change in total utility associated with the consumption of additional unit of a good. Now, let's consider this figure here. We have an indifference curve U1 and the consumer consumes good X or good Y. Let's first look at the initial point A. As we move down along this indifference curve from point A to point B, we say that this involves some loss of good Y and a gain of good X. Now, since point A and point B are on the same indifference curve, which implies the same utility, it simply means that the utility we've lost from consuming less of good Y should be equal to the utility we gain from consuming more of good X as we move from point A to point B. Mathematically, we can rewrite this as MUX multiplied by the change in X plus MUY multiplied by the change in Y. And since the utility along the indifference curve is still the same, then it means that the change in the total utility is equal to 0. In this equation, this bit MUX is the utility gain from additional consumption of good X. This bit MUY is the utility lost from consuming one less unit of good Y. This bit, which is the change in X, is the quantity of X that is gained. And this bit is the change in Y, which is the quantity of Y that is lost. Now, the Greek letter delta used here is to represent the change in a variable. All that we are saying here is we've lost some Y to gain a bit of X as we move from point A to B. But we notice that even with this rearrangement, utility has not been lost. So utility is still constant. So that is why it's equal to 0. We can rearrange the equation above. When we do this, we have MUX multiplied by change in X equals to minus MUY multiplied by change in Y. Now, if we go further, we have MUX divided by MUY, which is equal to minus change in Y over change in X. Notice that this bit here is simply the negative slope of the indifference curve, which represents the trade-off between good X and good Y. What does this mean? Since this is the negative of the slope of the indifference curve, and we know the slope of the indifference curve to be equal to marginal rate of substitution, then what we have shown here is this minus change in Y over change in X is equal to marginal rate of substitution YX, and this is equal to this bit over here, which is MUX over MUY. Now, what this tells us is that the marginal rate of substitution is equal to the ratio of marginal utilities everywhere along the indifference curve. Recall that if we have an interior solution, then in equilibrium, our marginal rate of substitution should be equal to the ratio of the two prices. So at interior solution, the slope of the indifference curve and the slope of the budget line are equal. So in that case, the slope of the indifference curve, which is MRS, and the slope of the budget line, which is the ratio of the two prices, should be equal. Now we can rewrite this equation then as marginal rate of substitution being equal to the ratio of the utilities as we have shown above, and this also being equal to the ratio of the prices, which is the slope of the budget line. So which means that we can characterize consumer equilibrium either in terms of marginal rate of substitution between the two goods or in terms of the ratio of their marginal utilities. One thing to note here is if we rearrange the equilibrium condition, it will give us a good intuition behind what we have here. We've seen that this equation shows us that the ratio of the utilities is equal to the ratio of the two prices. Now we can simply rewrite this by cross multiplying here, and we arrive at MUX divided by PX, MUY divided by PY. This bit is marginal utility per dollar spent on good X, and then this bit is marginal utility per dollar spent on good Y. So this equation says that in an equilibrium, a bundle maximizes total utility only if the marginal utility of the last dollar spent on each good is the same. To understand this better, suppose that a consumer chooses a bundle where the condition above does not hold, and we have marginal utility of Y divided by PY being less than marginal utility of X divided by PX. This means that the consumer can increase total utility by simply spending one more pound on good X and one less pound on good Y. So this is because each pound spent on good X gives the consumer more utility than each pound spent on good Y. So reallocating spending towards X away from Y will increase overall utility even though total expenditure hasn't changed. Now, similarly, if the consumer were at a point where MUY over PY is greater than MUX over PX, he could increase his utility without spending more money simply by switching a pound away from X to good Y. To summarize, when the marginal utility of the last dollar is the same for each commodity, then there is no way that income can be reallocated between goods as to increase total utility, which implies equilibrium. So this is all that we have on our lesson on consumer optimization, focusing on utility. Our next lesson will be an algebraic approach to all that we've been learning so far on consumer choice. If you enjoyed today's lesson, consider subscribing. Thank you.